Our next application of integration has to do with finding work done in a particular situation. The basic method we'll use to approach problems involving work is the same as the basic method for finding volumes of revolution, arc length, or total mass from a varying density. We first split the problem into pieces we know that are going to approximate the situation. In this case, we'll be splitting up the problem into pieces for which we can calculate the work done. Then we'll figure out the work done on each piece, or the contribution of each piece. We'll approximate the solution by adding up all of the contributions of each piece. We'll then pass to an exact solution by taking a limit as the number of pieces goes to infinity. And then at the end, we'll recognize that what we've done is set up an integral, and that's an integral we will then evaluate using the fundamental theorem of calculus and one of our previous techniques, or by using Wolfram Alpha or maybe a handheld calculator. So a quick review of what we mean by work. This is work done in the physical sense, which means if we have a constant force acting in the direction of motion, the work done is force times distance. Depending on whether we're using English or metric units, the units for work will either be pounds of force times feet of distance, or foot-pounds. Or in the metric system, we would have newtons of force times meters of distance for Newton meters, or joules. The particular kind of problems we're going to focus on in this class are problems where we're lifting some weight a given distance. For these problems, our work done will be the weight times the distance lifted, so we'll be using foot-pounds for the most part in here. As a quick example, if we have a 5-pound book, we lift it 4 feet off the floor, we've done 5 times 4, or 20 foot-pounds of work. One thing to keep in mind is that work done in the physics sense is not the same as effort. So for example, if we walked over to a wall and pushed on it as hard as we could for an hour, we will have expended a lot of effort, but if the wall doesn't move, we will have done no work. So we must move something a given distance in order for work to be accomplished. So this gets complicated and requires the use of an integral. We'll split the problem into pieces we know that approximate the situation and that we know move a roughly constant distance. If they move a roughly constant distance, then we know how to find the work done on each of the pieces. It'll be the weight of the piece times the distance moved. That in turn allows us to approximate the total work done in the situation by adding up the work done on each piece. We pass to an exact value for total work by taking a limit as the number of pieces goes to infinity. Finally, we recognize the solution as an integral and then evaluate it using either our techniques from Chapter 7 or a computer. Our first example using an integral to find work done is for us to figure out the work required to empty a full tank of water by pumping the water out of the top of the tank. Here our tank is a cylinder standing on its base. It's got a height of 10 feet, a radius of 3 feet, and we have to recognize that the complication in this problem is that because we are pumping water out of the top of the tank, water at different heights in the tank gets pumped different distances. So to figure out the work done, we first need to slice the tank up into slices that are pieces we know that are going to be pumped roughly a constant distance. In other words, the water contained in the slice all moves about the same distance to get pumped out of the top. In this case, those slices will once again look like discs that are parallel to the base of the tank. We want to figure out the work done on each of those slices, which means we first figure out the weight of one of the slices and then multiply by the distance that slice is going to be pumped. In other words, the distance to the top of the tank. the weight of one of my slices is going to be the volume of a slice, which we know how to find, times the weight density of water. So we need to know the volume of the water, and then we multiply by 62.4 pounds per cubic foot, and we get the weight of one of the slices. Once we have that, we multiply by the distance that slice has to move to get up to the top of the tank. The volume of a disk is something we've done many times. So the volume of one of our slices will be pi times r sub I squared times the thickness delta hi. We're in luck here, though, because the figure has, since it's a cylinder, it has disks that all have the same radius. They're all equal to the radius of the cylinder, which is 3. So the volume of each slice will be 9 pi times delta hi. So no similar triangles or Pythagorean theorem this time. So here we just note that the radius of the full tank is 3, and we'll go ahead and put in the height of the tank as well, which we know to be 10 feet. All right, back to the work done on a slice. Since we know the volume of a slice, the work done will be the volume times the density. That gives me the weight of each slice. And we multiply that by the distance that we have to move the slice of water to get it out the top of the tank. Now, if we come over to the figure, notice that to get from the slice up to the top of the tank, we have to move a total of 10 minus h sub I feet. Right? The disk of water here, the slice is sitting h sub I feet above the base, and since the total height is 10, that means we have 10 minus h sub I feet left to go. So the work done on that particular slice of water would be 9 pi delta hi, its volume, times 62.4, its density, times 10 minus h sub I, the distance it has to move. Now, following our usual procedure, we note that the total work done on that cylinder full of water would be roughly the sum of the work done on each of the slices. And we'll save a little time and not write that in, because we'll just be rewriting the work on a slice over and over. The total work then would be exactly what we would get if we took a limit as the number of slices went to infinity. In that case, each slice is getting thinner and thinner, so we're doing a better and better job of approximating the total work. And so we'll take the limit as n goes to infinity of that summation. So the crucial step is to recognize that what we are doing is setting up a Riemann integral that represents the total work done by emptying the cylinder full of water. So we're going to integrate. The smallest value h can take is 0 if the slice was sitting at the bottom. The biggest value h could take would be 10 if the slice was sitting all the way up at the top. The function we get from our work that we did on each slice, and the delta hi becomes the dh, pointing out what the variable of integration is. This integral turns out to be not so bad. We can pull the constants out front, make it a little bit easier to look at. So we're integrating the function 10 minus h between 0 and 10. Using the fundamental theorem of calculus, we can see that that integral would be, or the antiderivative of 10 minus h would be 10h minus h squared over 2. We've got to evaluate that between 0 and 10. If we plugged in 10 for h, we'd get 100 minus 10 squared over 2 would be 100 minus 50. So that would give us a total of 50, because when we plug in 0, we would get 0 So we need 9 pi times 62.4 times 50. That's going to give me my total work. I can approximate that with a handheld calculator. And I'm going to get about 88,216 foot-pounds of work required to empty our tank full of water by pumping the water out of the top. Our second example of using an integral to find work has to do with kind of a common Calculus 2 sort of problem where we're lifting something from the ground up to, say, a rooftop using a chain. So the roof is 12 feet above the ground. We've got a metal plate at the end of our chain weighing 100 pounds, and the chain itself weighs 5 pounds per foot. Now when we are hoisting this plate up to the top of the roof, we're doing work on the plate, which is being lifted 12 feet, but we're also doing work on the chain, because as we pull, right, we're lifting both the chain and the plate. So the total work done in this problem will be the work we do on the steel plate plus the work required to lift the chain. And it's the chain that's kind of the tricky part, because a link of chain at the very top doesn't move very far, but a link of chain down by the steel plate moves about 12 feet. A link of chain in the middle would move about 6 feet. So each piece of chain is actually moving a different distance, and that's why it requires an integral for us to figure out the total work done on a chain. Now the work done on the plate would be 100 times 12, so 100 pounds times 12 feet would give us 1,200 foot-pounds. And then as noted, the work that we do on the chain has to be represented by an integral because different pieces of the chain move different distances. So let's set up the work done on the chain as an integral. We have to slice the figure into pieces we know that are going to move roughly a constant distance. So I'm just going to take a tiny length of chain that I'll call delta y sub I, and I'm going to define y as dropping down from the roof down to that piece of chain. So to figure out the work done on that piece of chain, I need to know how heavy the piece of chain is and how far it moves. So the weight of one of my slices of chain will be its length, which is just the delta y sub I in this case, times the weight density of the chain, which is 5 pounds per foot. That gives me the weight of the slice as delta y sub I times 5. Right, that delta y is a tiny little length of chain. If the weight density is 5 pounds per foot, the weight of the slice is 5 times delta y. And because of the way I've defined my variable y sub I, the distance I lift that particular slice is just y sub I. Altogether, the work done on one slice of chain will be 5 times y sub I times delta y sub I. I can approximate then the total work done on the chain by adding up all of those little pieces, or adding up the work done on each of those little pieces. I'll represent doing that by the summation sign, and as we've been doing the last few examples, we won't continue to write the work done on each piece over and over. We'll note that if we increase the number of pieces to infinity, we would be doing a better and better job of approximating the work done on the chain. So we'd get an exact value by taking the limit as n goes to infinity of our summation of all of the work done on all of the pieces. And then we recognize that what that has done has we have defined a Riemann integral for the work done on the chain. We're integrating the function 5y dy, and we note that the smallest y could be for a piece of chain up at the top. It'd be 0, or it could extend all the way down to the plate, which would be a distance of 12. An antiderivative for 5y is 5y squared over 2. Evaluate that between 12 and 0 gives me that'll give me 360 foot-pounds of work required to lift the chain. So the total work done in the problem would be the 1,200 foot-pounds required to lift the plate, plus the 360 foot-pounds required to lift the chain, for a grand total of 1,560 foot-pounds of work done to lift the plate up to the roof. And that concludes the example. This concludes our presentation on using integrals to find total work done. In our next chapter, we'll start taking a look at what we call sequences and series. I'll see you next time.